Hello friends, now let us solve a cantilever problem which carries point loads and UDL load as given in figure. We will find shear force and bending moment values at different segments or different sections, and then we will draw the shear force and bending moment diagrams. The usual sign conventions are given here. We will follow that. Now, as a first step, what we have to do? We have to divide the beam into segments, right? Between loads, you have three loads. So, one segment, second segment, third segment, and fourth segment. So, let me name it A, B, C, D, and E. First, let me take the first segment CB, right? We will find shear force and bending moment parallelly. Okay, so first the segment is CB. I pass a section which is X distance from free end. To the right, downward is positive. So Vx 2.5 kilonewton, it is a constant. So between CB it is constant. Between CB it is constant, or the shear force is constant. Now we will find the bending moment mx. Right side counterclockwise is positive. Here this force 2.5 kilonewton will produce clockwise moment. So negative 2.5 is the force. What is the perpendicular distance? X is the perpendicular distance. It is a linear, right, law. Then apply the boundary condition at x equal to 0, m b equal to 0, at x equal to 0.5 meter. I am at C, substitute 0.5, so minus 1.25 kilonewton meter. Right. So for the first segment we have found the shear force and bending moment. Now let us move on to the second segment. So I will take this X 0.5. I am passing a segment section here X, right? Now this UDL load has to be changed into point load. It will act at the mid. 1 kilonewton meter is the uniformly distributed load. What is this distance? It is X minus 0.5. So 1 into X minus 0.5 is the shear force, right? So between DC Vx 2.5 plus, because this is the section, to the right I have one shear force, one external force, another external force. So I will add both x minus 0.5, and it is a linear expression. So at x equal to this segment DC, x starts from 0.5, ends at 2.5 meter. So 0.5 meter, we substitute, we are at C, and we are getting 2.5 kilonewton. At x equal to 2.5 meter, we are at D, we are getting 4.5 kilonewton. Right? Now we will move on to the bending moment. Tc mx. Right. To the right, I have two forces. I have to find out the bending moment. 2.5 clockwise into x. So minus 2.5 into x minus 0.5 is the force. What is the perpendicular distance? This is the perpendicular distance. What is this distance? This distance is x minus 0.5, then it is half of that value. So x minus 0.5 by 2 is that perpendicular distance. So x minus 0.5 is the force. Perpendicular distance is x minus 0.5 by 2. You can multiply or keep it as such. Definitely it is going to be higher order. So it is parabolic. Now I am going to substitute the boundary condition. At x equal to 0.5 meter, I am at C. So MC is minus 1.25 kilonewton meter. If you substitute, you will get it. At x equal to 2.5 meter, I am at D. If you substitute 2.5 here, 2.5 here and 2.5 here, you will get 8.25 kilonewton meter. Right? I have obtained the shear force and bending moment for two segments. Now we will move on to the third segment. So what I will do, I will delete all this. When we move on to the third segment, you see here, this entire UDL load is up to D only, right? Beyond that D, we don't have that UDL load. So what I will do, I will change this UDL into point load, which will be acting at the mid, right? One is the UDL and 2 is the distance. So 1 into 2, it is going to be 2 kilonewton. I am passing a section here and taking x. Now I want to find out the shear force and bending moment between ED. So ED, right. To the right, I have two forces. Vx 2.5 plus 2 equal to 4.5 kilonewton. So between ED, whatever force we got up to D will be present. Okay, it is constant. So we will find out the bending moment now. Mx, force 2.5 into x minus 2.5 into x, then it is also minus, it is 2. What is the perpendicular distance? What is this distance? It is half, it is 1. So this distance is 1 meter and this is 0.5, so 1.5 meter. Then this is going to be the perpendicular distance. This is going to be the perpendicular distance. So x minus 1.5. This is going to be x minus 1.5. X minus 1.5 is the perpendicular distance, and it is a linear variation. So at x equal to 2.5 meter, I am at D. So MD is 8.25 kilonewton meter. At x equal to, we are here, it is 4 meter. It is x equal to 2.5 meter. So 4 meter, I am at E. So I am getting 15 kilonewton meter. Substitute, you will get it. Right? So we have obtained the shear force and bending moment for the segment ED. Mind it always, this expression is valid only for that segment ED. Now we will discuss the fourth segment or the final segment. I am passing a section, right? Now I will find shear force and bending moment. AE Vx. To the right, I have 1, 2, 3 forces. So 2.5 plus 2 plus 3 is 7.5 kilonewton. So at E and at A. So we got the value. It's a constant, right? It is a constant. It is a constant. Now the bending moment AE, the bending moment mx, we have three forces, 2.5 clockwise, 2 clockwise, 3 clockwise. Perpendicular distance for 2.5 is x minus, for perpendicular distance for 2 kilonewton, the perpendicular distance is 2 into x minus 1.5. For the third one, this is the perpendicular distance. Up to this, it is 4, x minus 4. This distance is x minus 4. So minus 3 into x minus 4. It is a linear expression. So at x equal to 4 meter, you will get the same. We are at E and it is 15 kilonewton meter. At x equal to 5 meter, I am here, x equal to 5 meter. The bending moment at A is, if you are substituting for 5 here, 5 and 5 here, you will get 22.5 kilonewton meter. So I have obtained all the shear force values and bending moment values. Now I am going to draw the shear force and bending moment diagrams. Let us draw now. So see here, all the values are positive. I am drawing it. A, B. As you know, whenever you see a point load, there will be a step in shear force diagram, right? So 2.5, between CB it is constant. So what is this value? 2.5 kilonewton, right? And then when you see uniformly distributed load, dV by dx equal to minus W. So when your W is constant over dc, your slope in the shear force diagram is going to be constant. So the variation is linear variation. See here, it is linear variation. So it is linear, it is a straight line. And between ED, there is no other force. So it is 4.5 kilonewton. Then another 3 kilonewton is added. So as we know, there will be a step. This is 3 kilonewton and this total is 7.5 kilonewton. And you can call it plus, right? Now we will draw the bending moment diagram. Bending moment diagram, all are negative values. So I am drawing here itself. AB. Now for bending moment, you have to use this expression dm by dx equal to V. When I see constant value in shear force diagram, you will have a linear variation in bending moment. When you have a linear variation in bending moment, a shear force, your bending moment diagram will be parabolic, one order higher, right? So you have a constant value, the slope is going to be constant. So between CB, it is straight line. The value is 1.25 kilonewton meter. Between DC, here it is linear and we have parabolic variation. The slope starts from with the same slope you have to start, and then the slope keep increasing or changing, and it is parabolic. And here the value is 8.25 kilonewton meter. After that you have linear variation. Linear variations, one linear, another linear, straight line. But the important point here is, in this junction there will not be slope change. Whatever slope it ends, the same slope we have to draw the shear force. This is a bending moment diagram, that is straight line, and here you have a step. Definitely there is a change in the slope. The shear force value is increased, so there will be a change in the slope. No space, that's why I have drawn here like this, but there will be slope difference. This slope and this slope are different slopes, and here the value is 15 kilonewton meter, and here the value is 22.5 kilonewton meter. All are negative. I hope you would have understood how to find the shear force and bending moment values, and how to draw the shear force and bending moment diagrams. Okay, you may ask a question, why we have to draw all this? We need to know the shear force bending moment values at any section in a beam. When we discuss bending stress and shear stress, you will understand why, right? Now you can very easily find these values, not by doing all these expressions and then applying the boundary conditions and so on. Very easily you can find the shear force bending moment values. How? See here, at B, shear force 2.5 kilonewton. At C, there is no other force between CB, so it is the same 2.5. You come here, you have two more added. When you have come to E, without the load, it is the same load. With adding 3 kilonewton, the load is increasing, the shear force is increasing. Okay. Similarly, for bending moment, at B, it is 0. At C, 2.5 into perpendicular distance. At D, 2.5 into perpendicular distance, 2 into perpendicular distance. At E, only two forces, but since the distance is increasing, the bending moment will also increase. 2.5 into perpendicular distance 4, then 2 into 4 minus 1.2, 2.5. Then at A, you have three forces, all three and its corresponding perpendicular distance. If you add, you can very easily get the shear force bending moment values. But the variation, linear, parabolic, linear, That can be obtained only if you have understood all this. If you just with the past experience, like if you see UDL, then there is straight line. If you see straight line in shear force diagram, then there is a parabolic variation in the bending moment diagram. These all could be possible only after gaining some experience. So I hope now you would have understood how to find out shear force and bending moment diagrams for combined loading. Next problem, we will add a couple also in the beam, so that what variation is going to come due to the effect of the couple we will discuss. If you have a doubt, you can mail me, contact me through the number which is given in the description, or you can leave a comment in the comment box. Thank you.